All right, today we're jumping into something pretty intense. The rapid-fire math the paramedics have to do every single day to save lives. And this isn't some textbook theory. We're talking about performing with absolute precision when the stakes are as high as they get. So let me ask you this straight up. If a life was on the line, right in front of you, could you do the math? Could you calculate the right dose of a critical drug? It's a heavy question, for sure, but for first responders, it's just another Tuesday. Just picture it for a second. The scene is chaotic, alarms are going off, and a person's life literally depends on what you do next. The doctor tells you the dose is based on the patient's weight, but the drug in your hand is measured totally differently. Get it wrong? And well, the consequences are huge. So let's break down exactly how they get it right, every single time. Okay, so how do they do it? Well, before you can solve any of these problems, you've got to speak the language. And in medicine, that language is universal, it's precise, and it all begins with the metric system. So pretty much everything in medicine is built on these metric units. We're going to be focusing on just two key things: weight, which is measured in grams, milligrams, and micrograms, and volume, which is in liters and milliliters. These are the absolute building blocks for everything that follows. Now, here's the first hurdle, especially in the US. We think in pounds, right? But drug doses, the really critical ones, are almost always based on kilograms. That means one of the very first things a paramedic has to do, often in just a few seconds, is make that conversion. You're not going to see a paramedic pulling out their phone's calculator, right? There's just no time. So they use this awesome mental shortcut. First, you take the patient's weight in pounds and just slice it in half. Then you figure out what 10% of that new number is. And finally, you just subtract that 10% from the halved number. That's it. That's their weight in kilograms. Let's walk through it with a 200-pound patient. Half of 200 is 100. 10% of 100 is 10. Subtract that 10 from 100 and you get 90 kilograms. It's simple, it's fast, and it's dead-on accurate for what they need. This isn't just a trick. It's the foundation for everything that comes next. Okay, so we've got the patient's weight in kilograms. Step one, done. Now we need to figure out how much medicine to give. And to do that, we have to crack the code on the drug vial itself. We need to understand concentration. So what is concentration? It's really just how much of the actual medicine is packed into a certain amount of liquid. A great way to think about it is it's the drug's strength, not its size. And you'll usually see it written as milligrams per milliliter, or mg/ml. And the best part? Figuring it out is usually super simple. You just look at the vial, take the total amount of the drug, and divide it by the total volume of fluid it's in. That's your concentration. So for example, if a vial of furosemide says there are 40 milligrams in 10 milliliters of liquid, you just do the division. 40 divided by 10, that gives you a concentration of 4 milligrams per milliliter. And what that means is that for every single milliliter you drop, you're getting exactly 4 milligrams of the drug. See? Super important to know. Okay, but what happens when you grab a vial and it doesn't say mg/ml? Instead, it just has a percentage, like dextrose 50%. Looks tricky, right? Well, there's a super easy trick for this. You just take that percentage number, turn it into grams, and stick it over 100 milliliters. So, take lidocaine 2%. That just means 2 grams per 100 milliliters. And since we know there are 1,000 milligrams in a gram, 2 grams is 2,000 milligrams. Do a little quick math, simplify 2,000 over 100, and boom, you get a standard concentration of 20 milligrams per milliliter. It's a slick conversion that gets you the number you need. All right, let's recap. We've got the patient's weight in kg. We know how to figure out the drug's concentration. Now for the main event, putting it all together to calculate the actual dose. And that's usually done in one of two ways. Now, there are two main ways you're going to give a drug. The first is a bolus, just a single dose, pushed all at once, bam. It's fast-acting and super common in emergency situations. The other way is a drip, where you give the medicine slowly over time. This gives you really precise control, which is perfect for very powerful drugs. Let's do the math for both. Okay, let's put you in the driver's seat. Here's a classic bolus problem. The order is to give 15 milligrams of diltiazem. You look at the vial and it says it has 25 milligrams of the drug mixed in 5 milliliters of fluid. So, the big question, how many ml do you pull into that syringe?
Okay, first things first, what's our concentration? The vial says 25 milligrams in 5 milliliters. 25 divided by 5, that's 5 milligrams per milliliter. Easy. Now the formula is super simple. It's the dose you want divided by the concentration you have. So for us, that's 15 milligrams divided by our concentration of 5 milligrams per milliliter.
And there's your answer, 3 milliliters. You drop exactly 3 mLs and you've nailed the 15 milligram dose. That's it, precision in a syringe. Okay, that was the bolus. Now for the IV drip, which has a few more moving parts, but it's totally manageable. Here's the situation. The order is to give nitroglycerin at a rate of 40 micrograms per minute. Your drug concentration is 200 micrograms per milliliter, and the IV tubing you're using delivers 60 drops for every milliliter. Your job is to figure out the flow rate. How many drops per minute? The formula looks like this. You take the desired dose, multiply it by your drip set, and then divide the whole thing by the concentration. So let's plug in our numbers. 40 times 60 divided by 200. Now check this out. It's kind of cool how the math works. The micrograms on top and bottom cancel out, the milliliters cancel out, and what are you left with? Just drops per minute, which is exactly what we need. You run the numbers, and you get 12 drops per minute. Exactly. That's how you make sure a patient gets a steady, safe dose of a really powerful drug over a long period of time. So we've walked through the language, the conversions, the calculations, the whole shebang. But let's take a step back for a second. What's the big picture here? Why is this so ridiculously important?
You know, it really comes down to a few key things. First, this isn't just doing math. It's about keeping a person safe, period. Second, if you can wrap your head around concentration, you've basically got the master key to solving almost any of these problems. And finally, getting this right, it's what lets a first responder walk into a totally chaotic scene and bring order and control to it. It's a game changer.
And that really leaves us with one final thought. In a world where the difference between helping and harming can come down to just a few drops of liquid, is there any skill out there more important than getting the math right?